Hello everyone, today I'm going to introduce our project 1. My name is Zhu Jiahao and my partner is Yang Han. First, the MOSFET characterization. The first two pages will be about gate voltage sweep. We derive from the sub-threshold current equation to this one, doing log, and you fit the curve around 0 to 0.5 volt, so we can get the slope, which is copper over UT, and also other parameters. And we look at where the current will rise to get the threshold voltage, which is 0.3 volts. For the PFET, it's the same case. Expect that the PFET subthreshold area is like 1.7 volt to 2 volt. And we can also get the threshold voltage of minus 0.7 volt. And then we'll do the source voltage sweep for the two type of MOSFET to get to the VT, the UT. Actually, we do like doing a log, then we just find the straight line and doing curve fit. For example, for NFET, we do like from 0.5 volt to 0.7 volt, and for PFET, it's like 2 volt to 2.22 volt. We both got very ideal result, and this is our summary. First, for the result, I think the I0 for the PFET is quite low because we got the result from curve fit. Exactly, I think the I0 will be like the 10 power of minus 12. In some cases, it's always very small. And basic transistor circuits, we are talking about common drain, common source, and OTA is a common drain, which is source follower. We'll have a linear gain of copper, and then a component is the reciprocal of V-in. And also the common source derived from the subthreshold current equation. We'll also get a linear small signal gain of minus copper over sigma. And also the residual part is also the reciprocal of the V-in. For the OTA, it's basically a low pass filter characteristic. So I will just assume that the V-in is the differential mode input, and the transconductance of the OTA is G, and we can get this kind of formula with capacitor load and load C and the resistor load R. And the source follower, we do the measurement of we just sweep the input voltage of the gate, and we do like 3 different DC voltages for the drain. Because the output, the transconductance, the transfer function is like copper minus something over V-in, but we actually saw that after the 1.2 volts, the follower began to function properly. The variation of the voltage of drain doesn't affect much. We have like the copper, the gain, linear gain of like 0.91 to 0.884 is very close number. And for example, for the variation of copper, because we can see from this transfer function that we can do like, because this part is basically, we think after something, we assume that this part is constant, the back part, and then we will use 2 points on the line to decide to get to the copper, and then this is modified copper curve later, and we can see that actually the copper curve is, I think it is more relevant to the VGS. It's not about VG or VS only. So this effect may be due to the voltage difference, which will change the potential barrier over the source side. So I think the copper is major depend on VGS, not only VG. And the common source, we do rough scan and the fine scan. I think it is a problem of the of the device because there is some steps here on our plot. I think it is because of the accuracy of the voltage we can get. Actually, if I want to get 1 millivolt, the program always crash. So basically, we do things like that because we can see the gain which I derive from the VDD minus V out over V in. It is exactly what it should be like because there is a reciprocal part of V in over here. Also we do a fine scan. Basically, it's the fine scan. If we just do the average, so its gain is more average, like around 11, and we can see the comparison is about the same. And it's the follower setup. I think we do first thing is linear follow-up. The linear follow-up is the same thing for the big bias current and the small bias current because the thing didn't change much. So the required slew rate is very small. But this kind of step, I think, is the same problem like the last one. It's accuracy problem, but it works very fine. And for the step, we didn't notice much difference between big bias currents and small bias currents. And for a very small step like 40 millivolt, it doesn't change much because it is like around 0.175 volt to 0.2 volt. So basically, the LPF just moves the input signal for both are offset, and then that's it. And we think the problem of not seeing the effect is the required slew rate. Actually, the Cmax can be like 10 times minus 11, so we don't see the effect, basically. Thank you.